The problem with looking at graphs to find a limit is that sometimes we're kind of guessing as to what the value is. We don't have an exact value. So it is beneficial a lot of times to be able to figure out a way to use algebra to find that limit. So this is climb time, and in this video, we're going to look at how to find a limit using algebra. So to start with, I want to take a look at plugging in as an option for finding a limit. So let's say we have the old parabola, the quadratic, looks something like this. The thing about the quadratic is it is defined everywhere. And so we could look at that value, we could look at this 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 value, we could look at any value along there. What happens is the limit coming from the left and the limit coming from the right will be equal everywhere, which is equal to the function value. So if I'm coming from the left and I'm coming from the right, it's going to be equal to the function value right there. And if I'm coming from the left to this point here, maybe it's -2. If I'm coming from the left, I'm coming from the right, they're going to equal the same function value, which is the function value itself. So plugging in is the first and easiest way to find a limit. So we can find the limit because it is often equal to the function value. It's not the same thing as the function value, but it's often equal to the function value. So that's important to recognize. So if we have a continuous normal function, the easiest way to find a limit is just to plug in. Now, if we look at this example right here, the limit as x approaches -1 of x squared minus 1 over x plus 1. It turns out that if we plug in -1 directly, we get -1 squared, which is +1. +1 minus 1 is 0. And then on the bottom, we get -1 plus 1 is 0. So we get 0 over 0. That's not good because 0 over 0 is considered indeterminate and it's not defined. If we were to graph it, though, and if you graphed it on your graphing calculator, you'd see it looks something like this. It looks very much like a line. It looks like the line x minus 1. In fact, I'll write that in. So it's similar to the line. No, I'm not going to write that in. We'll look at that later. It's similar to line x minus 1, but the difference is that there's a discontinuity right here at -1. And the reason why there's a discontinuity right there at -1 is because if I plug in -1, as we just looked at, we get an undefined value. So it's not defined at -1, but it's defined everywhere else. And it looks just like a line. And the question is, how do we figure out what that line is? So the answer to that question is we reduce. So we're going to go through that real quick here. So we're going to reduce this. So if I say equals limit as x approaches -1, and then what I'm going to do is I see the numerator is a perfect square, so it can be factored. So if I factor this perfect square as x minus 1 times x plus 1, and in the denominator, I have x plus 1. I'm adding parentheses, not sure why. But anyway, there's parentheses just so maybe it makes it more obvious that these two things are the same. But this is how you factor a perfect square. So you get, if this is a squared minus b squared, you get a minus b times a plus b. If you were to FOIL that out, you would get that over there. So this is how you factor perfect squares. And the reason why we want to do that is perhaps we can see now that this will cancel with that. These two, when you divide this by this, you get 1. 1 times anything is itself. And so that's why we're able to cancel those two out, because anything times 1 is itself. So, but before we cancel it out, what I want to point out is if I plug in -1 now, plug in negative down there in the denominator, I get 0. If I plug in -1 in the numerator, I have the same problem. -1 minus 1 is -2, but then I get 0 over here, so I get 0 over 0. So I still get 0 over 0, which is still an issue. So I can't plug in until I first cancel out. But these two do cancel out. And so I end up with the limit as x approaches -1 of x minus 1. So basically, the line x minus 1 is not the same thing as the original function. They're very similar to each other, but they're not the same thing. In fact, I want to actually write that in. X squared minus 1 over x plus 1 is not the same thing as x minus 1. They are not equal because they don't have the same y values for all x. So they're not equal for all x. However, they are equal for all x except for -1. And so because the limit itself doesn't care about the function value where we're evaluating it, it turns out that this limit is in fact equal to this limit. These two limits are equal. The two functions are not equal, but the two limits are equal because we don't care about the x value. Or sorry, we don't care about the function value at -1. So because we don't care about the function value at -1, we can actually reduce, and these two limits are equivalent because the only thing that keeps this one up here from being equal to this one right here is the function value at -1. And the function value at -1 is not our concern when we're finding a limit. So now we can plug in. So the limit as x approaches -1 of x minus 1, just now we can plug in. So we get -1 minus 1, which is equal to -2. So the limit is -2, and we can find it by reducing first, then plugging in. So again, that works because while this is not directly equal to this, like these function values are not equal, the limit of this is equal to the limit of that. And that's because the only thing that keeps these two from being the same, actually they are the same for every value except x is -1. So I'm gonna write that in as well. So x squared minus 1 over x plus 1 is in fact equal to x minus 1 for all x except x is equal to -1. Okay, it looks like going off the screen a little bit. I'll write it over here. All right, so it's true for all values of x except x is equal to -1. So because we don't care about the function value at -1 when we're finding a limit, that allows us to reduce and then plug in. So reducing and plug in works.
All right, now we're going to look at another example. This one's the limit as x approaches 0 of square root of x plus 1 minus 1 over x. We're interested in the same sort of process. We want to be able to simplify. If plugging in doesn't work, we should plug in first. Let's plug in first. Plugging in 0, I get the square root of 0 plus 1, which is the square root of 1 minus 1. Well, the square root of 1 is 1. 1 minus 1 is 0. I get 0 over 0. So plugging in gives me 0 over 0. So that's not going to work. That's a no-no. So we need to find a way to simplify this and then plug in, because that'll give us an exact value for the limit, which can be very useful to know the exact value. If we can put it into a graphing calculator and we can actually look at points, we can probably predict what that value is going to be. But sometimes, it's hard to know exactly what that value is, and it's good to have a method to find it precisely. So let's do that. Let's see if we can find it precisely. So what we're going to do in this case, instead of factoring it, because it's not obvious how to factor this if it's factorable at all, we're going to use a method called multiplying by the conjugate. So the conjugate is basically the same expression, except instead of a minus sign here, we're going to multiply it by a plus 1. Now this is x here, so this is the original expression here, and we want to multiply the numerator by the conjugate. Now, here's the thing. I can't just multiply an expression by some random expression because that will change it, and we don't want to change it. We're trying to figure out what the limit as x approaches 0 of that is. So I can't multiply the numerator by something and not expect to change it. So what I got to do is multiply both the numerator and the denominator by the same thing, because if I do that, then I'm not changing it. And the reason why I'm not changing it is because this is 1. I can multiply anything by 1. That's okay, because when you multiply something by 1, you get itself. So I cannot expect it to stay the same unless I multiply by 1. So whatever I do to the numerator, I have to also do to the denominator. Now the question is, why the conjugate? Why are we multiplying the conjugate? So the conjugate again is this. It's you have a binomial here, an a minus b, and so we want to multiply it by a plus b. If this were a plus b, we want to multiply it by a minus b. So the conjugate is the same a and b, but instead of a minus, you have a plus. So if this were plus, that'd be a minus. So the reason why we want to multiply by the conjugate is that the conjugate will cause the square roots to disappear, but only in the numerator. And the reason why the square roots disappear is if I multiply this first term by the last term, that's the outer. So if I multiply the outer, the O in FOIL, and the inner, the I in FOIL, so if I take the outer and I add it to the inner, you get the exact same term, except one is positive, one is negative. And that happens every single time if you have a minus and a plus. So therefore, the outer and inner terms will cancel out. And then the first term, because you're multiplying by itself with a square root, the square roots will disappear. And negative 1 times positive 1 is also does not have a square root because there's no square roots in it to begin with. So the multiplying by a conjugate is a known way of getting rid of a square root. Um, but that only works in the numerator. In the denominator, that's another story. So let's see what happens. Let's give it a whirl. So the limit as x approaches 0. In the numerator, I get square root of x plus 1 times the square root of x plus 1. Well, that's going to be x plus 1 because the square roots cancel out there. The outer and the inner, they cancel out. And so negative 1 times positive 1 is negative 1. So you end up with x plus 1 minus 1 and when after we FOIL the numerator. In the denominator, we have x times square root of x plus 1 plus 1. That's what we have in the denominator. Now, you could distribute the x if you wanted to, but it turns out you need to factor back out again. I happen to know that ahead of time, so that's why I didn't distribute the x. But hopefully you'd see that you could factor it back out after you distribute it back in. Because the reason why you would want to factor it back out is because this goes to 0, and then what we have is an x in the numerator and an x in the denominator, and those two actually cancel each other out. Um, and so that's why if you had distributed it, you'd have to kind of factor it out again to see that those two cancel out. So this cancels with this. And what we get, what we're left with, is the limit as x approaches 0 of 1 all over square root of x plus 1 plus 1. Now, the reason why we have a 1 in the numerator there is because we had x over x, and x over x can be reduced to 1 over 1. So there's a 1 here, and there's 1 multiplied by what's in parentheses there, which is itself, so we can get rid of the parentheses. So we end up with this. This is equivalent to this. Now, they're not equivalent for all x, as we mentioned before. They're equivalent for all x except for at x equals 0. So once you make this cancellation with variables like that, you have to recognize you've just reduced the domain by which these that you could work with. So we can work with all the values of x, we just cannot work with 0 anymore. But that's okay, because with limits, we don't care about the function value itself at 0. We just care about all the values around 0. So all the values around 0 should be the same for this one and the original, or this one, or this one. So all the values around x will be the same for all of these. They just will not be the same for 0 itself. But that's okay, because we're talking about a limit. So now let's plug in. So if I plug in, I'm going to get 1 all over the square root of 0 plus 1 plus 1. And so the square root of 0 plus 1 is 1. So end up with 1 all over the square root of 1 plus 1. And square root of 1 is 1. So get 1 over 1 plus 1. So end up with 1/2. So it turns out that the limit as x approaches 0 of square root of x plus 1 minus 1 over x is 1/2. And you could arrive at that conclusion by looking at a calculator, but this is the algebraic way to do it. It gives you a precise result. So as a reminder, we can find a limit by plugging in directly, but if we get an undefined value or an indeterminate, which is also another type of undefined value, then we can try to reduce and then plug in. And after reducing and plugging in, if that works, then that is what the limit will be. And again, a reminder why that works is because while this original expression is not totally equal to this expression, because they're not equal to each other for all values of x, they are equal to each other for all the values of x near 0, but not at 0. So specifically, this is not equal to this when x equals 0. But this is equal to this for all values around x equals 0, and that's why the limits are in fact equal.